In section 5.7, we're going to look at the natural log function for integration. We recall that we've already covered the power rule for integration before, and the power rule said the following, that the antiderivative of x to the n dx is equal to x to the n plus 1 divided by n plus 1 plus our constant of integration. We also saw that this rule held for all integers, all real numbers, n, other than n equals to negative 1. Which asks the question then, what happens when n is equal to negative 1? In other words, what is the antiderivative of x to the negative first, which is going to be the antiderivative of 1 over x dx. Well, we recall that the derivative of the ln of x was equal to 1 over x, and therefore the antiderivative of 1 over x is going to be the ln of x plus c. Notice that technically speaking, it's not just the natural log, but it's actually going to be the natural log of the absolute value of x plus c. We can investigate this further, but let me just say this, that if you consider the integrand, 1 over x would have domain all values of x except 0. So 1 over x is defined for all values of x except 0. In particular, it's also defined for the negative values of x. However, the domain of the natural log would be x strictly greater than 0. Natural log is not inherently defined for negative values, but if we put the absolute value on it, then it will work out. Of course, we could look at the kind of u substitution chain rule style version of this. The antiderivative of 1 over u du is going to be equal to the natural log of the absolute value of u plus c. So this will give us a new method for u substitution. If we have an integrand, and in particular, if you notice that you have a fraction whose denominator is present, and also whose derivative of the denominator is there, then sometimes we will be using the substitution, let u be the denominator of the expression, and that will lead us to a natural log integration. For example, in number 1, we want to find this particular antiderivative. First thing we can do to make life a little bit easier is we kind of have a constant coefficient of a half. So we can use our constant multiple rule to pull the 1/2 outside of the antiderivative. And now this is our new basic rule. The antiderivative of 1 over x is going to be the 1/2, the natural log of the absolute value of x, plus our constant of integration. So 1/2 ln of the absolute value of x plus c. Let's take a look at number 2. Use the log rule for integration. We want to find the antiderivative of 1 divided by 4x minus 1 dx. This particular example isn't a simple 1 over x as the last problem was, but we do have a denominator here. Let's try letting u, we're going to do a u substitution, let u be the denominator. So u is going to be 4x minus 1. When we do that, our du is going to be equal to 4 dx. Well, we have a dx to substitute out for our du, but we would also require a 4. We've covered this before, that this is the situation where it's always easy. As long as you're out by a constant in terms of your du and dx, you can always multiply and divide by that constant to get the substitution to work. So I can put that multiplication of 4 on the inside of the antiderivative if I multiply by 1 over 4 on the outside. Under this substitution, here's what we get. This is going to be 1/4 the definite integral of this 4 dx. 4 dx, that's going to be du. I'll write it off to the side. I'm going to have a 1 in my numerator. It's a multiplicative factor, that's all that's left. And then our denominator, 4x minus 1, that was u. So this becomes 1/4 the antiderivative of 1 over u du. And this was the whole intent and purposes of doing the substitution, is that we have now transformed this into a basic antiderivative in the variable u. We can apply our antiderivative rule. The antiderivative of 1 over u du is the natural log of the absolute value of u plus c. And then, as with any u substitution problem like this, we always need to back substitute to return to the original variable x. Everywhere we see a u, we can replace it with 4x minus 1. So there's our answer. It's 1/4 the ln of the absolute value of 4x minus 1. Let's take a look at example 3. They ask us to find the area of the region bounded by the graph of y equals x divided by x squared plus 1, the x-axis, and the line x equals 2 to 3. So again, whenever you have to draw a graph of something like this, we can kind of just go ahead and do the graph first. So we have x divided by x squared plus 1. And the graph looks something like this. It's going to be bounded by the graph of y equals x divided by x squared plus 1. The x-axis, so the x-axis is here, and the line x equals 2 to 3. The area that we're interested in finding is going to be this area here. And in order to find that area, we can set up an integral for this, a definite integral. The shaded area goes from 0 to 3 on the x-axis, and it's the area under the curve of x divided by x squared plus 1 dx. So this definite integral represents the area of the region described in this question. In order to find the value of this definite integral, we want to do a u substitution. Let's let u be the denominator. Let u be x squared plus 1. Then our du is going to be equal to 2x dx. I already have on the inside of the integrand the x dx. All we need is a factor of 2. We can accommodate for that. I can multiply by 2 on the inside if I multiply by 1 over 2 on the outside. So we're going to do our u substitution on this. This is going to be equal to, we have our 1/2, the definite integral of, I'll come back to this in a moment. Here's our fraction. The 2x dx, well, wherever I see 2x dx, I can use that to put du. And then the denominator, x squared plus 1, that was our u. So it becomes equal to 1/2 the integral of 1 over u du. We've seen this before, but whenever you do a u substitution on a definite integral, not only do you have to substitute out the integrand, but we also have to change the bounds as well. So our original bounds were from x equals to 0 to x equals to 3. We need to change these in terms of bounds of now the new variable u. And to change those, you just simply use the defining substitution equation for u. U is x squared plus 1. Therefore, when x is 3, u is going to be 3 squared plus 1, which should be 10. And when x was equal to 0, u is going to be 0 squared plus 1, which is going to be equal to 1. So our new bounds in terms of the definite integral for u is going to go from 1 to 10. The antiderivative of 1 over u is going to be the natural log of the absolute value of u. This is going to be evaluated from 1 to 10. This is equal to 1/2 times the ln, the absolute value of 10, minus the ln, the absolute value of 1. We have the natural log of 10, and then the absolute value of 1 is 1, and the natural log of 1 is going to be 0. So the final answer is the area under this curve is going to be equal to 1/2 the ln of 10. That's the exact answer. If you wanted an approximation for this, that would be approximately if I can get my calculator out. Well, I'll tell you what, I'll just leave that up to everybody. But you can obviously punch it in and give it to any level of decimal precision you would like. Take a look at one more. Let's take a look at example 4. We are asked to recognize the quotient forms of the log rule. So in example 4, part A, we're asked to find the antiderivative of 3x squared plus 1 divided by x cubed plus x dx. Again, this is a quotient. It's not recognized easily as the antiderivative of some elementary function, but what we would notice is that I see a piece of this integrand whose derivative is also present. And it's that kind of thinking that guides our u substitution. I noticed that if I let u be the denominator again, so let u be x cubed plus x, then the derivative of that part of the integrand is simply going to be 3x squared plus 1 dx, and that entire thing is going to be our numerator of this integrand. Therefore, this will fit perfectly into a u substitution. This is going to be the antiderivative of, everywhere I have that 3x squared plus 1 dx, I can replace that with du. I now have a 1 left in the numerator as a multiplying factor. And then the denominator, x cubed plus x, that's what we let be our u. So under the substitution, it simplifies to the antiderivative of 1 over u du. This we know is going to be equal to the natural log of the absolute value of u plus c. And then simply back substitute. The antiderivative is the ln of the absolute value of x cubed plus x plus c. Let's do a few more of these. In example B, again, things you could try here. I wouldn't advise it on this one, but if you get stuck and you have tangents, secants, and cosecants, the old school trigonometry trick would say change everything to sines and cosines. However, in our calculus class, we know that there's a relationship between tangent and secant squared. Namely, secant squared is the derivative of tangent. So we can let u be equal to the tangent of x. Our du would then be secant squared x dx. And this substitution is going to fit perfectly. Secant squared x dx, that's equal to du. And the denominator was our u. We let u be tangent of x. So we get the antiderivative of 1 over u du. This is, again, the natural log of the absolute value of u plus c, which is equal to the natural log of the absolute value of tangent of x plus c. Let's take a look at part C. We want to find the antiderivative of x plus 1 over x squared plus 2x. Going with the running theme of this section, let's let u be the denominator. Let u be x squared plus 2x. Our du would then be 2x plus 2 dx. So it's not what we have in the numerator, and you got to be very careful here. We are allowed to multiply the integrand by a constant as long as we multiply by the reciprocal, or essentially divide by that constant on the outside, in order to keep things the same. You cannot, in general, just add things or subtract things into the interior of an antiderivative. It doesn't work like that. However, if I look at x plus 1, then we come down here to my du, this term actually has a common factor of 2. If I factor that out, then essentially I see is that du is really equal to twice x plus 1 dx. So we are fortunate that we are in this scenario where we are only off by a constant. I can multiply by that constant 2 on the inside if I put a 1 divided by 2 on the outside. With those constant factors multiplied in, we now can do the substitution. This is going to be 1/2 the 2 times the quantity x plus 1 dx. That's going to be our du. So it's 1 over u du. This is going to be 1/2 the natural log, the absolute value of u plus c. And then when we back substitute, we get 1/2 the natural log, the absolute value of x squared plus 2x plus c. Let's take a look at one more. We can do a log integration on this. Let u be 3x plus 2. Our du is going to be 3 dx. So I can multiply on the inside by 3. If I put a 1 over 3 multiplication on the outside, this will give us 1/3 the antiderivative of 1 du over u, which is going to be 1/3 the natural log, the absolute value of 3x plus 2 plus c.